So, in this lecture we will start with Fourier series. So, before we start the Fourier series, if you are an electrical engineering student, in the signal and systems theory you have you know what is a signal. Signal is as basically a real valued or complex valued function. We will just define what is a signal in a systems theory. If you have some system like this, kind of imagine a black box. So, you give the input and what comes out is the output. So, this black box you call it a system, and input is a function. So, you give for all times. So, let us say input I of t. So, it is an input O of t, or let us say E of t. This is electric signal you can think. So, that is you give this input and you get the output as E of t. So, for each at each times you give I, you get E if it is a real valued. So, this is coming through going through a system. So, that can be governed or described by differential equation or some other thing. Okay. So, it is linear or non-linear. That is this is so basically for each IT. So, for an input you have an output. So, that is a real valued function kind of. A signal is, I will just define what is a signal. Signal, so let us say f of t is a real valued, a real or complex valued function of time. So, if it is a real valued, that is a simple. So, if it is complex, so it takes so any complex number, if I just recall, z is a complex number which you can represent with R2. So, you can put it in the plane. So, as x plus iy, x y belongs to real. So, this in a different form, that is Euler form. This is the length of this complex number, amplitude of the complex number into e power I. This is the theta, is the angle. Okay. So, this is the Euler representation of the complex number. So, you have f of t, which you call so you have a different kinds of signal. So, it is a real, if it is a real valued or complex valued function, we call it signal. Okay. So, we start with the Fourier series of what is a Fourier series. So, basically we deal with this real valued or complex valued function we want to represent in terms of fundamental signals. So, what are the fundamental signals? So, for example, if you know what is a signal like this, if you from this system, some simple fundamental signals are sin t, sin let us say omega t, cos omega t. Omega is the frequency. Okay. These are the fundamental signals. Okay. So, you want to represent general signal, so or general function f of t in terms of these fundamental signals. Okay. So, different types of signals you have. So, if t is the time, continuous time variable, so you call continuous signal. If t is discrete time, so it is called a discrete signal. Okay. So, this system, so let us say L is the operator, so which is a system L acting on I of t, the input. If it is a linear, so L is linear, so linear system. When do you say it is a linear system? L is linear, if so usual way. So, if you can take a linear combination of the inputs, two inputs C f1 plus f2, if this is same as if you give this as the input, what comes out is the C comes out as a constant, this is output for F1 signal, F1 input plus output for the input F2. So, if this is the case, then we call this a linear system. So, what you give input is actually your signal. So, that is the real or complex valued function, which is maybe continuous or discrete depending on whatever it is. Okay. So, depending on whether it is a discrete signal or complex continuous signal, if it satisfies this, you say that it is a linear, the system is the described system is a linear if it satisfies this. As I said in the introduction, so in natural sciences and engineering sciences, most of the phenomena are repetitive. So, for example, as you can see, vibration of a string in mechanical system, or in electromagnetic signals emitted by transmitters in satellites, they are all repetitive. So, this is basically a repetitive process in the repetitive phenomena in natural and engineering sciences. So, mathematically we can put this as so we call this the system. So, that phenomena, the input or the outputs the signals, okay, we can represent as periodic function. So, that gives, because they are repetitive in nature, natural, so many phenomena are repetitive. So, they are basically vibration of a string, all this, okay, pendulum of a clock in a mechanical system, in electrical voltage and current in electromagnetic systems, okay, voltage and currents in electrical networks. These are all repetitive. So, you basically in the nature what you have is these signals are basically time periodic. Okay. So, that means between 0 to t or time t, the signal is repetitive after t2. So, what is it just repeats with two time period t. So, 0 to t you have a signal. So, you have a different thing and it repeats from t2 to t and so on. So, such signals we can represent as periodic functions. Mathematically they are periodic functions. So, a function, so definition for this periodic function is a function is periodic if f of a function f of x, f of t is periodic if f of t plus, you give this period is same as f of t for every t. Such a functions are periodic functions. You know many of these periodic functions. For example, sin t, cos t, all these are periodic functions. Sin t, sin cos t, sin omega t, cos omega t, these are, as I said, is fundamental signals. They are also fundamental signals. They are fundamental functions. Sin t, cos t, these are all periodic functions. So, if I have f of t which is periodic, a periodic function f of t. So, let us draw this, how it will be. If it is repetitive, how does it look? So, if it is 0, if it is 0 to t, let us say so like this. Okay, what happens at t to 2t? So, again it is repetitive again, so same way. So, like this minus t to 0 also, so repetitive like this and so on. So, such a repetitive process what you see in the nature, they are actually periodic functions. So, can we represent such functions? As I said in the introduction, we will do this Fourier series, which is actually a kind of transform, Fourier transform, which takes. So, Fourier transform on periodic functions is actually a Fourier series, Fourier coefficients. So, which is a Fourier transform, and its inverse transform is basically what you get is Fourier series. Okay. So, we will see what it is before we define what it is. So, Fourier coefficients we will define. For a time signal f of t, we will just define what is Fourier coefficients. So, you start with periodic function, let f of x be a periodic function. With period. So, instead of calling it as a function of time, I am just write now onwards I will just write f of x as in a mathematical symbol. So, we will use a function of f of x, which is as a kind of, you can imagine as a signal with x as a time variable. So, f x be a periodic function with period L, let us say. Then what is its frequency? If it is if it is a repetitive. So, if it is repetitive like this as a periodic function, then the frequency of this frequency of the signal of f of x is, so W naught. So, we call this fundamental frequency, which is 2 pi by L. So, you can think of you can think of a sine function. So, sine function like this, which is 0 to 2 pi is the period. So, on par with this, if you on par with the sine functions, so fundamental signals, those sine and cosine functions, if you imagine. So, 2 pi by that their time period is 2 pi. So, whose frequency is 1. So, fundamental frequency is 1. So, the sine 2t is also periodic function, but whose time period is 2 pi by whose time period is pi. So, this is 2. So, you have like this, it will go on. So, frequency is 1 and 2 depending on what you have here. So, so we will define this is this, then the frequency is defined like this. This is the fundamental frequency, fundamental. Why you call this fundamental, we will come to know a little later. So, Fourier coefficients, I will define what is a Fourier coefficient. The Fourier coefficient defined as some integrals. So, I am just giving, so for each n, so I am just defining for each n, which is from 0, 1, 2, 3 onwards. For each n, you define a n with so I will define it as an integral 2 by L minus L by 2 to L by 2 f x. So, there is a time signal. So, this is what is the input you have given. So, this one, so the signal you take and you multiply with these cosines and sines. So, cos periodic functions, those are fundamental periodic functions, cos n omega naught. So, omega naught is this of x dx. This is the function of x. With this you multiply and you integrate from minus L by 2 to L by 2 because of its period is L. Okay. Imagine you have a, so it is defined from minus L by 2 to L by 2. This function is defined over L by 2, and my L by 2 to plus L by 2 plus L, again it is repetitive, whatever is the function here is repetitive because of periodic function. So, a n is this and b n, if I define like this 2 by L, now this is f x. Now, we multiply with sine n omega naught x dx. So, what are these? These are kind of frequencies. So, this is n into W naught is a fundamental frequency, n W naught is a second frequency. So, and so on. Okay. This is the first frequency, this is the second frequency, n equal to 2, you have n equal to 0, it is just a constant. Okay. So, this is our fundamental frequency, and you have n omega naught, n equal to 2 onwards there are other frequencies. So, these are if they exist, these are Fourier coefficients when they exist. What do you mean by when they exist? So, this integral should make sense. So, f is such a signal, such a periodic function for which you multiply with cosines and sine, it should be integrable. So, you should be able to integrate, this integral value should be finite. So, all these a n and b n should be finite for n equal to 0, 1, 2, 3 onwards. So, what is actually happening? So, once you define what is, these are the Fourier coefficients. So, this is actually a transform. So, what you are going is a time signal to some discrete values, n is from 0, 1, 2, 3 onwards. So, you have a time signal, so that you break it into frequencies, so discrete frequencies. So, here these are a n's and b n's, these are the discrete frequencies. Okay. So, n is basically n is 0, 1, 2, 3 onwards. Okay. So, n into w naught, these are the frequencies for discrete frequencies, n is because n is running from 0, 1, 2, 3 and so on. So, omega naught starting with n equal to 1 is a frequency, fundamental frequency, 2, 3 and so on, you will get different other frequencies. So, how many? They are all discrete because n is running from 1 to infinity or 0 to infinity. So, you have a periodic function which is a time signal, and you break this into discrete frequencies. Okay. Frequencies, those are all n w naught. So, if I write like this, so there is a 1-1 correspondence. So, what is this 1-1 correspondence? So, you have a periodic function f x or the time signal, and this side what I get, you are given you have given f x the time signal, what you get is Fourier coefficients, Fourier coefficients. You have Fourier coefficients here. So, these are a n's and b n, so n is from 0, 1, 2, 3 and so on. So, you have if you are given if you give this input as f x, okay. So, what you get is Fourier coefficients, these are these things. So, now so these are this is your Fourier transform on a periodic function. So, these are your Fourier transforms, also called Fourier transforms, Fourier transform of f of x, a periodic function f of x. So, these a and b n's are basically they define Fourier transform of a periodic function. So, once you get a Fourier transform, they are in the discrete space, the discrete numbers. Okay. Now, the question is, so basically you go from a time signal to a discrete frequency signals, right. You break it into different frequencies. Right. So, what happens is, so you should be able to retrieve back whenever you want, after some process you want to retrieve it back. Is it possible to do that? Yes, that is answer is yes. So, you will be able to come back from, if you are given a Fourier coefficients a and b n numbers, a0, a1 and so on, and b0, b1 and so on, if you are given, if you know all these Fourier coefficients, some numbers, these are simply numbers, you should be able to reconstruct your f of x. So, that is a Fourier series. So, your transformation is from the periodic function you define Fourier coefficients as your Fourier transform, and inverse transform is if you are given, so these frequencies, discrete frequencies, if you know with these discrete frequencies you should be able to reconstruct. So, if you are given this with these discrete frequencies, you will be able to reconstruct your signal f of x. So, that is Fourier series. So, this way is a Fourier transform. So, other way, so this is inverse Fourier transform, inverse Fourier transform, or here because periodic function, in this case inverse Fourier transform is nothing but Fourier series, Fourier series. So, what is this? How does this look? So, I can just reconstruct f x as in terms of this a n's, b n's and the fundamental functions or fundamental signals like cosines and sines. So, a0 divided by 2 plus sigma n is from 1 to infinity, you have a n cos n omega naught x plus b n sin n omega naught x. So, this is a Fourier transform. This is Fourier transform. This is the Fourier series. So, if you know a naught, a n and b n. So, if you are given here, you can get your function f x in terms of these just by multiplying sine and cosine functions. Okay. Sine and fundamental signals like fundamental functions sine n omega naught x and cos n omega naught x. You multiply and take this series. This sum is actually converges pointwise to f x under some conditions on a function f x. So, what are those conditions? So, you have to see, right now we do not know exactly. So, if your period, not all periodic functions you can get like this, but under some sufficient conditions, under certain conditions on f, under certain conditions on periodic function, it is always possible. This Fourier series you can always see, given any function f x, periodic function f x, you can always define a Fourier transform. Just that is Fourier transform is this Fourier coefficients you can always define. Only thing you have to make sense is these integrals should be finite. Okay. So, as long as these integrals are finite for all such functions f x, so for all such signals, general signals, you can simply get the Fourier coefficients. So, one transform, you are transforming these to discrete space, and then you should be able to come back, then only it makes sense. So, that is the inverse Fourier transform, that you only once you go to that, once you transform something, you should be able to come back, then only it is useful. So, to get a Fourier series, that means once you define these Fourier coefficients, using them you can derive this Fourier series, but that should be giving you your function. When is the question is, when is that the Fourier series actually is actually originally is your signal f of x, original function f of x, original periodic function f of x. So, under some conditions, under some sufficient conditions, on f x, this star is true for each x, for each fixed value of x. You fix x, this is a series of numbers that converges to some number that is exactly equal to f of x once you fix x. Okay. So, what are those conditions? I will just give you briefly. So, if f is piecewise continuous, if you know what is continuous function, I hope you all understand what do you mean by know what is I hope you all know what is a continuous function. Continuous function is if you know the calculus, you must be knowing continuous function. Piecewise continuous function I define, piecewise continuous function. It is a continuous function as a pieces. Okay. If I give you for example like this, between let us say a to b, a function, if it is like this is piecewise continuous function. So, what happens, you can think here. So, piecewise continuous function is, it has a finite number of places, you have a discontinuity, a continuous function. So, a function with finite number of discontinuities. So, those discontinuities are also, so you know the discontinuities are of many types. So, one is 1 by x is discontinuous at x equal to 0, at x equal to 0 this goes to infinity. Okay. So, that is also discontinuous. So, these are, but they are defined at that 0, at 0 it should be finite. So, these are jump discontinuities, they are jump discontinuities. That means, so wherever it is discontinuous, at those values both left hand side and right hand side, the function is a finite value, function is defined, limit of those functions. Here this side limit f of x is this value, and this side limit is the value here. So, they are finite values. Okay. So, you have a finite number of discontinuities, a function with finite is called is a piecewise continuous function. Roughly this is the definition. Okay. So, we will define formally later when as we require. So, this is one condition. So, piecewise continuous, this is a one sufficient conditions, but this proof is required. If you have a signal f of x that is piecewise continuous function like this, then the Fourier coefficients you can always define, because this is a continuous pieces of finite number of pieces which are continuous functions. You know those integral values, these integrals are finite for such function, this is always finite. So, Fourier coefficients are well defined. Using this Fourier coefficients you make the sum that is always converges pointwise to f of x. Pointwise means you fix your x, that value is actually equal to the signal value at x equal at such fixed value of x. Okay. So, if it is a piecewise continuous function, this is always true, but the proof is a little difficult. But what we prove later on is if a piecewise a smooth function. So, that means continuously a differentiable function. This means f of x. So, if you have f is a piecewise continuously differentiable function, if f dash of x is a piecewise continuous function. As you see, f dash of x is defined at every point between a to b and the points a and b. F dash is defined everywhere, okay, except at those points. So, those limits left hand sides of left hand limit of f dash. F dash at b means the definition of the derivative. What is the derivative of f dash of x at b? At x actually you see f of x plus h minus f of x, this is the definition of derivative. So, h as h goes to 0. So, this is the if 0 plus or minus both are same, okay, 0 means 0 both plus or minus 0. If you take plus, that is x right side, x plus h. So, you basically you are looking at the derivative at this point. For example, you are looking at x is value here, this is x plus h, right. So, you have this side, this is the derivative. So, derivative from the right side at this point, so derivative this side. So, that limit this side, and if you take h goes to 0 minus, that is you finally get x minus positive h, you are taking the limit here. So, you are looking at the tangent at this point, okay, the limiting value here for this function here. So, f dash of x which is defined everywhere, is f is differentiable at all those points. First of all, it should be defined, it is differentiable at every point, okay. So, f is differentiable, and if you look at the derivative of f x, f dash derivative of f, that is f dash of x, that is piecewise continuous function, okay. If then f is piecewise differentiable function, piecewise differentiable function. Okay. So, continuously you should not use piecewise differentiable function is if f dash is a piecewise continuous function, then we say that f of x is piecewise differentiable function. So, if this is the case, if your signal f of x is a piecewise differentiable function, then you can easily show that this Fourier series is actually converging to the signal f of x at every point x. Okay. So, I will prove this maybe in the next video. So, what we so later videos we will try to prove this result. Now, we will just take some function f of x, periodic function f of x. So, how do we look at the periodic functions? Now, we will just we will take some periodic function, we will try to calculate this Fourier series, and we can actually see that we will just find the Fourier series, and if you for the time being, if you assume this result under these conditions, if piecewise differentiable function, if f is piecewise differentiable function, you can always assume that, so you can believe that f is this series, whatever you calculate, this one, that actually converges pointwise to f of x. This we will actually prove it in later videos. Right now we will take some f of x, we will try to calculate the Fourier coefficients a_n's and b_n's, and then we will make this series. That series is actually converging to f of x if you believe these sufficient conditions. Okay. So, let us consider example to evaluate this Fourier series. Let us consider f of x as mod x, for example in the domain between -1 to 1. So, if you plot this, it looks like 0, -1 and 1, let us say 2, and this is -2 and so on. So, if you look at this, it looks like 1 to 0 and this looks like 0 to 1. So, this looks, mod x looks like this clearly. So, if it repeats, because it is a periodic signal, so it actually repeats it goes to 0, at 2 it is 0, then it goes up to 1 and so on. So, we will go on seeing that repetitive pattern. That is how you define this mod x over full real line as a repetitive thing. So, this has a period 2, this has a period 2. So, what we have is what we have stated is this function f x is actually involving this Fourier coefficients. For example, a0, so as I said earlier, a0 by 2 plus sigma n is from 1 to infinity a n cos n omega naught x plus b n sin n omega naught x. Omega naught n x, omega naught is a fundamental frequency. So, omega naught is actually 2 pi by this period L, that is pi. So, where ANs are actually 2 by L, L is 2, this is from -1 to 1, and you have f x cos n, omega naught is pi. So, you have n pi x dx. So, this is including n is running from 0 1 and so on, and Bn is you have 2 by L is a period, here it is 2 again, it is -1 to 1 f x times, now we have a multiplication function is sin n pi x dx. So, again n is running from 1 to 3 onwards. So, if you keep n equal to 0 here, that is 0. So, there is no contribution for Bn, n equal to 0. So, if what we do is we just calculate this ANs and BNs. Okay. So, and then we get this series, and that series we claim this converges to this function f x, which is mod x in the domain -1 to 1. So, let us calculate this ANs. So, n equal to 0. So, A naught is simply -1 to 1, f x is mod x, cos 0 is 1 dx. So, if I actually see this, this is 0 to 1 x dx, and negative side this is minus x. So, -1 to 0 mod x is minus x. So, I have this dx. So, if I actually calculate this, it is x square by 2, this is half minus of minus half. So, that makes it 1, and n is running from 1 to 3 onwards. You have this a n, we can calculate the same way. So, we have -1 to 1, f x is mod x cos n pi x dx. So, this is again you can expand this mod x 0 to 1 x cos n pi x dx minus -1 to 0 x cos n pi x dx. So, do the simple integration by parts. If you do, sin n pi x by n pi is the antiderivative of this cosine cos n pi x, and then x. So, these are the boundary terms, they have minus 0 to 1, 1 by n pi comes out, sin n pi x, and then you have a derivative of x is 1 dx. Do the same thing for the here. So, you have a sin n pi x by n pi times x. Now, we substitute minus 1 to 0, and you have minus minus plus 1 by n pi minus 1 to 0. So, derivative of x goes, so we have a sin n pi x dx. So, this is equal to, so sin n pi, that is 0, and because of, so this will be 0, and again you have this is 0. So, there is no contribution here, and here this you can see minus 1 by n pi. So, minus minus, so antiderivative is minus cos n pi x by n pi. I put 0 to 1, and here again, so you have plus, so you get minus here, minus 1 by n pi cos n pi x by n pi. This is running minus 1 to 0. So, if you actually calculate this, this is 1 by n square pi square, cos n pi is 1, minus 1 power n, cos n pi is minus 1 power n, minus cos 0 is 1, and you have here again n pi whole square, that is n square pi square, cos 0 is 1 minus, so cos minus n pi is cos n pi, that is again minus of minus 1 power n. So, this if you see, this is minus, this is minus minus plus, you put it here minus, and this is plus, these are same. So, you have finally 2 by n square pi square minus 1 power n minus 1. So, this is what is the a n for n is running from 1 to 3 onwards. And the same way you can calculate b n, minus 1 to 1 mod x sin n pi x dx, and this is equal to 0 to 1 x sin n pi x dx minus minus 1 to 0 x sin n pi x dx. If you calculate this, evaluate this by integration by parts. So, minus cos n pi x by n pi x, you substitute these limits, minus minus plus, you have 0 to 1 cos n pi x by n pi dx. And the same thing you can do it here, minus minus plus here, cos n pi x by x times x. Now, substitute the limits minus 1 to 0 for this integral, and this is going to be minus, and you have minus 1 to 0 cos n pi x by n pi dx. So, as you see, cos n pi, this part is minus 1 by n pi, cos n pi is minus 1 power n minus 1, minus 1, that is 0 because of x. X, if you substitute x equal to 0 to 1, this is 0. So, you have only this, and what about this? This is minus of minus 1 power n, this is n pi, n pi, and you have a minus 1 that makes it plus. So, this gets cancelled. So, they do not contribute, and what you have is 1 by n square pi square, and this is sin n pi x between 0 to 1, and you have here minus 1 by n square pi square sin n pi x between minus 1 to 0. So, this will be sin n pi 0, sin 0 0. So, this both are 0. So, that makes it 0. You can easily see this because mod x is basically a even function, is even function. So, you can clearly in that case Bn has to be 0 because from -1 to 1 it has to be 0 because of the even function. So, integrand you can see it is even and this is odd. So, odd function odd integrand function. So, when you have -1 to 1 that has to be 0, that is clearly the case. Okay. So, n is running from 1 to 3 onwards. So, now you have this fx, that is mod x. This is what is still believing, we have not proved that that this Fourier series is converging to this series. A0 is 1, that is what we calculated. So, you have half plus sigma n is running from 1 to infinity. Ans are 2 by n square pi square minus 1 power n minus 1 times cos n pi x. So, this is between -1 to 1. So, this series I claim to converge pointwise to this function mod x. Okay. So, this is how when you are given a periodic signal f x, what you know now is only Fourier coefficients a n's and b n's you calculate and you compose this Fourier series, and once you have this series we claim that this series is actually converging pointwise to the function given periodic signal f x. Okay. In this case here it is mod x within the domain -1 to 1. So, this is what we have seen here. We still have to believe that this is actually true, and we will eventually prove in the later videos that this actually converging pointwise to the function wherever it is continuous. At discontinuous points we just have to take both limits, this side and that side of the limit, and you take the average of them. So, that is what we will eventually see that Fourier series is actually converging to the function f at the continuous points. At discontinuous points of course, we consider only jumps, finite jumps. So, you can just take the average of this jump, that is where it converges. Okay. So, this is what eventually we see in the later videos. So, we will stop here, and the next video we will continue to do more examples on this Fourier series. Thank you very much.